In this lesson, we're going to go through determining the area under a curve, given the equation of the curve and the interval over which we're looking for that area. Now, this is an application of a definite integral, a mathematical application of definite integrals. So we're going to be using definite integrals in order to determine the areas under a curve. Now, determining the area under a curve depends on the position of the curve of the function with respect to the x-axis. So as you can see here in case 1, we're considering the case where f of x is positive. Now, we've already seen in the lesson on properties of integrals that if the lower bound is smaller than the upper bound of the definite integral, then if f of x is positive, then the integral, the definite integral, is positive. So it's in fact for that reason that area under the curve really depends on the position of the curve with respect to the x-axis. So in this case 1, we have f of x to be positive. You can actually see here in black the curve corresponding to the function f that is continuous over the interval ab. So f of x being positive over the interval ab, then the integral from a to b of f of x dx is in fact positive. And the area under the curve, as you can see here as shaded in gray, is equal to that integral. So when f of x is positive, the area under the curve is defined by the integral from a to b of f of x dx. However, if f of x is negative, now f of x is negative when the curve representing f is below the x-axis. So when f of x is negative, according to the properties of definite integrals, then the integral from a to b of f of x is negative. However, we cannot have a negative area. So for that reason, whenever we have f of x to be negative over the interval ab, then the area represented here by the shaded region is in fact the opposite of the integral. So the area is defined by negative the integral from a to b of f of x dx. So that is when all the curve of the function is located below the x-axis over that interval. So the integral being negative, then negative the integral becomes positive, which gives me a positive area because the areas cannot be negative. However, if over the interval AB, as you can see here, if over the interval AB, the curve changes position with respect to the x-axis. Referring to this graph as an example, as you can see here, the curve crosses the x-axis at the point of abscissa C. And between A and C, the curve is above the x-axis with the region shaded as A1. And then between C and B, the curve is below the x-axis with A2 as the shaded region between the curve and the x-axis. However, here, in order to determine the area, since between A and C the curve is positive, then this area A1 is defined by the integral from A to C of f of x dx. However, between C and B, the curve is below the x-axis, therefore the integral from C to B of f of x is negative, so the area A2 is defined by negative the integral from C to B. So the total area here would in fact be the integral from A to C of f of x minus the integral from C to B, because from A to C it's positive, so the area is exactly the integral. However, from C to B it's negative, so the area would be the opposite of the integral, and then we just add them. By the way, it's good to note that when we say the area under the curve. The area under the curve is in fact the area that is enclosed between the curve and the x-axis. So the area under the curve when the curve is negative is not what you have below the curve. In fact, it's the area between the curve and the x-axis. So that is something I forgot to mention at the beginning. So anyway, so combining all these cases together, so what do you notice we're doing here? If f of x is positive, then the area is exactly the integral. When f of x is negative, then the area is the opposite of the integral. That in fact reminds me of the definition of the absolute value, because the absolute value of a is the same as a when a is positive, while it's the opposite of a when a is negative. So which leads me to this rule for combining the three cases we just discussed together as the definition for the area under a curve. So the area under the curve of f over an interval AB is in fact defined by the integral of the absolute value of f of x between a and b. Now, please, that is not the same as the absolute value of the integral. Please note that this is not the same as the absolute value of the integral, because in fact over here what we're doing is considering the area under the absolute value of the function. For example, here if we were to just look at it quickly, okay, if I had this curve over which I want to find the area under the curve, which means it's the area enclosed between the curve and the x-axis between a and b. So what we're doing here is that because between a and c the function is negative, so what we're doing is determining the integral from a to c and then multiply it by negative because of the definition of the absolute value. Because in fact, if we were to graph, if this is the graph of f of x, then the graph of the absolute value of f of x, where f of x is positive, the two graphs confound, while when f of x is negative, the curve is reflected with respect to the x-axis. So over here in red, I have the curve of y equals to the absolute value of f of x, while in black, I have the curve of y equals to f of x. So in fact, to determine the area under the curve, if this is the area we're looking for, now over here, since this is positive, for example, suppose that this has an area of 4 units squared. Well, this being negative, suppose it has an area of, not an area, but the value of its integral between a and c is -2. Then in that case, when we consider the absolute value, because of the symmetry, in fact, between a and c, if the integral here is -2, then the integral here would lead to an area of 2 units squared. And then over here, since the curve remained unchanged because of the fact that it's positive, then it would have remained 4. So by considering the integral of the absolute value of f of x, in that case, we would in fact have 2 plus 4 equals to 6 units squared as a total area. However, if we consider the absolute value of the integral, the absolute value of the integral would in fact consist between a and c here. Between a and c, it would have a value of -2, and between c and b, it would have an absolute value of 4, and this is what you're in fact putting in an absolute value. So that would be the absolute value of the sum, which for the area, this is not what I want. What I want for the area is in fact to have the absolute value of -2 plus the absolute value of 4 in order to determine the exact area. So if the area here is 2 because the curve is below the x-axis, the integral would lead me to a value for the integral equals to -2. So this is what I need to put in an absolute value in order to determine the exact area. So please keep in mind that to determine the area under a curve, what you need to do is integrate the absolute value of f of x and not look for the absolute value of the integral, because they're two totally different things. Now, if we move to just solving some examples here. In this first example, we need to determine the area bounded by the curve of f of x equals to x cubed plus 1, x equals to -2, and x equals to 1. If I were to graph the function y equals to x cubed plus 1, as you can see, I already have its graph here. So this is the curve of y equals to x cubed plus 1. So we need to determine the area under the curve between x equals to -2, this is -2, and x equals to 1. As you can see that the curve over here, this is the area under the curve between -2 and -1, and this is the area under the curve between -1 and 1. So as you can see on the curve, on the graph, that the curve is below the x-axis between -2 and -1, and the curve is above the x-axis between -1 and 1. So the area between -2 and 1 of the absolute value of f of x would in fact lead me to the integral from -2 to -1 of the opposite of f of x. Since over here it's negative, so we do multiply this integral by a negative. And then between -1 and 1, since it's positive, then it would remain plus the integral from -1 and 1 of x cubed plus 1 dx. And then we integrate each, not forgetting that we have a negative here. So it's 1 over 4x to the 4 plus 1, sorry, this is a plus x. So the integral of x cubed is 1 over 4x to the 4, and the integral of 1 is x. So that is between -2 and -1. And plus, it's the same function, so it's the same antiderivative, except it's the bounds that are different. And now what I do is evaluate upper bound minus lower bound for each case in order to determine the total area. Of course, not forgetting the negative we have here. So for x equals to -1, that's -1 to the 4, which is a 1. So that's 1 over 4 minus 1. Minus the lower bound. At the lower bound, -2 to the 4. -2 to the 4 is, in fact, a 16, a positive 16 over 4. So that's a 4. So not forgetting here that we're grouping them together. So this is for the lower bound. So it's minus the whole thing for the lower bound. Plus, now for the antiderivative between -1 and 1, upper bound minus lower bound, minus into, now for the lower bound, -1 is 1 over 4 minus 1. And then using your calculators or whatever, you could just calculate what this is equal to. And that should give me a 19 over 4 unit squared as a total area under the curve between -2 and 1. Now, suppose you had the same question, but you did not really have the curve of the function, or you were working on a paper without a calculator, without your GDC. So in that case, how could you really determine the sign of the function? So we do not start integrating before studying the sign of the function. So over here, we know that first, in order to study the sign of a function, we need to first start by determining its roots. So x cubed plus 1 equals to 0. Then x cubed is -1, which gives me a solution of x equals to -1. Now, x equals to -1 is inside the interval that we're looking at. So we do know that the curve changes sign over that interval. So we do start by setting up a table of signs of the function. So this is a function that is defined over all R. It's a polynomial function. So over here, we know that x cubed plus 1 is 0 at -1. Now, before -1, for example, if we were to evaluate this at -2, -2 cubed is -8 plus 1, that's -7, so that is negative. Well, after -1, for example, for x equals to 0, because 0 is in that interval, 0 plus 1 is 1, that's positive. So we can see that before -1, the curve is negative, and after -1, the curve is positive. And the interval that we actually have is here. -2 is before -1, while the other bound is 1. So that is the interval that we're actually looking at. So you can see that between -2 and -1, the curve is negative, and between -1 and 1, the curve is positive. So you would in fact need a table of signs in order to determine the sign of the function over the interval if you do not know the graph of the function and you had no access to a graphic calculator. Okay, so that is regarding the first example. Now, if we were to move to the second example, we have here a piecewise function. So we have f of x to be defined by x plus 4 over the interval -4, -1, and by 2 minus x over the interval -1, 2. Now, by looking at the curve obtained by this piecewise function over the interval -4, 2, so between -4 and -1, we have graphed the line y equals to x plus 4. Now, this is the line y equals to x plus 4, but we only consider the part of it between -4 and -1. Well, this is y equals to 2 minus x, but we only consider the part of the line between -1 and 2. So over the interval -4, 2, this is the curve that is formed by this piecewise function. And we're asked to determine the area of the triangle formed by this function over this interval, first using the formula and then by integration. So this is more or less in order to check that the integrals do give me the area under the curve. So over here, if we look at this triangle, we have a triangle and we know that the area is base times height over 2, which graphically we can easily see how many units is the base and how many units is the height. So if we consider this to be the height, we can see it's 3 units. And the base is between -4 and 2, so that is a total of 6 units. So it's half into 3 into 6, which gives me a 9 units squared for the area. Now by integration, now since we're dealing with a piecewise function, you can see that both lines that we considered, the two parts of the lines we considered, are in fact above the x-axis. So the area under the curve would be formed by the area under each of these two lines. So, however, at -1, the equation of the curve changes. So this is why here we need to, in fact, split the integral. So over here, the area would be defined by the integral from -4 to -1 of x plus 4 dx, of course. And it's a plus. It's a plus because both curves are positive. And then between -1 and 2 of the other line of equation 2 minus x. So it's -1, 2 of 2 minus x dx. And then we integrate each and we should end up with a total area of 9 units squared. So over here, integrating x plus 4, we have half x squared plus 4x. That is between -4 and -1 plus 2x minus half x squared between -1 and 2. Evaluating upper bound minus lower bound for each. So at -1, it's half minus 4. That is for the upper bound of the first one. Minus at the lower bound, -4 squared is 16. So that is an 8 minus 16 for the lower bound. Plus, over here, upper bound, that is a 4 minus 4 over 2, that is a 2, minus into -2 and minus half. So over here, simplifying, now you notice that we do have a half plus half, which is a 1. So let's just evaluate the rest. So it's a plus 1 minus 4, that's a negative 3, plus 8, that's a 5, okay, and that a plus 2, that's a 7, and then a plus 2, that is a 9. So that is a 9 unit squared. So you can see that the integrals did in fact give me the exact area as given by this formula. Of course, if you have a triangle which you can easily determine the length of the base and the height or the sides in order to determine the area, just like this case here, you could in fact do that in order to give the area. However, if the question asks to determine it by integration, you can be sure that the integration in fact gives you the area you are looking for. Now in this last example, we're back to the function of equation y equals to x cubed plus 1. Now over here, there's a small twist into this question where they do ask for the area bounded by the curve, the y-axis, and the lines y equals to 1 and y equals to 9. So this is y equals to 9, and this is y equals to 1, and it's bounded between the curve and the y-axis. So this is the area we're looking for. However, the integral would in fact give you the area between the curve and the x-axis. So over here, as you can see, this point is of abscissa 2. So the integral from 0 to 2 would in fact give you the area under the curve, which I shaded in red. However, in the question, they're asking for the black area. So there are two methods in order to solve this exercise. So whenever they're asking for the area between the curve and the y-axis, what you can do is determine the corresponding value of x, and then this is method 1, and then the area, the black area, is in fact the area of the full rectangle minus the red region. So in order to determine the area, the black area here between the curve and the y-axis, what you need to do is determine the area of the full rectangle and then subtract from it the area under the curve, which is given by the integral from 0 to 2. So over here, the area of the full rectangle, over here I have 2 units, and here I have 9 units. So the total area of the rectangle is in fact 2 times 9, which is an 18. So the area is 18 minus the integral from 0 to 2 of the function x cubed plus 1 dx. Now over here you can see that over 0 to the function is above the x-axis, so that integral is in fact positive. Okay, so now all I have to do is determine this integral here and then subtract it from 18. So that is 18 minus 1 over 4 x to the 4, that's the antiderivative of x cubed, plus x, and that is between 0 and 2. So 18 minus. Now over here for the upper bound, I have a 16 over 4, the upper bound being 2. I have a 16 over 4, which is a 4 plus 2, and then this is for the upper bound, and then for the lower bound it is a 0. So that is an 18 minus 6, which is in fact a 12. So that's 12 units squared for the area enclosed by the curve and by the y-axis between y equals to 1 and y equals to 9. However, there is a second method in order to solve such a question, and the choice of the method which one to go for, whether it's the rectangle minus the area under the curve or the second method that we're just about to see, really depends on the function and which one is easier. For example here, if it's now, let's just first start by discussing method 2. Now in method 2 consists of working with the inverse function. So as you can see here, this is the area we are in fact looking for. This is the area that we determined using method 1. So as you can see, between 0 and 2, the function is 1 to 1. It's always increasing and it's continuous. Therefore, the inverse of this function exists. So, and that is the inverse of the function. So if that is y equals to f of x, then this is y equals to the inverse of f of x. Of course, that is the inverse of the function between 0 and 2. So you can see here that this is 2, 3, 4, 5, 6, 7, 8, 9. So you can see that the area enclosed by the curve between y equals to 1 and y equals to 9 is in fact the same as the area enclosed by the inverse of the function between x equals to 1 and x equals to 9. So in fact, the choice of which method to choose really depends on the function. If it's easier to find the integral under f of x than to find the integral under the inverse of f of x, then you'd go for method 1. You'd find the area of the total rectangle and then subtract the area under the curve. However, if it's easier to work with the inverse function, in that case, what you would do is find the expression of the inverse and then find the integral or the area under the inverse, the curve corresponding to the inverse between x equals to 1 and x equals to 9. So over here, to find the inverse function, we have y equals to x cubed plus 1. This is our original function, so we start by solving for x. So x would in fact be the cube root of y minus 1. So f inverse is in fact the cube root of x minus 1. That is the curve. That is the equation of the curve corresponding to the inverse function, of course, when x is greater or equals to 1. Now, as you can see here, it is easier to integrate f of x, so method 1 is easier. However, this is still doable. So over here, if I were to determine the area, so I would consider the area between 1 and 9 of the cube root of x minus 1 dx. Now this is still doable because the expression inside the cube root is in fact linear. We could use the compound formula here. So the integral between 1 and 9 of x minus 1 to the 1/3 dx. Now we do know that the integral of x to the n dx is 1 over n plus 1 times x to the n plus 1 plus k. Now that's the antiderivative, that's the indefinite integral. However, over here, instead of x we have x minus 1, and of course for n equals to 1/3. So what I would do here is replace in the antiderivative x by x minus 1, and I do not forget to divide by a, which is the slope of the linear expression. However, here it happened that a is 1. So applying the power rule with the compound formula for n equals to 1/3, that would give me a equals to, now for n equals to 1/3, and 1/3 plus 1 is 4 over 3, so that's 1 over 4 over 3, then x minus 1 to the 4 over 3, and all of that between 1 and 9. So simplifying that would in fact give me 3 over 4 into x minus 1 to the 4 over 3. We could just bring back the cube root if we wish. So it's the cube root of x minus 1 to the 4 between 1 and 9. So applying upper bound minus lower bound in order to evaluate that. So that's 3 over 4 into. Now over here we have for 9, for x equals to 9, that's 9 minus 1, which is an 8. So that is a cube root of 8 to the 4 minus 4x equals to 1, that is a 0. Now we know that 8 is in fact 2 cubed, so the cube root of 2 cubed is a 2, and then to the power of 4, that is a 16. So that is a 3 over 4 into 16, which is a 3 times 4, which is a 12 units squared. So you can actually see here that we did obtain exactly the same area, and these two areas are in fact equal because of the symmetry with respect to the line y equals to x. So by the symmetry with respect to the first bisector of the coordinate system, I would in fact end up having this area equals to that area. So in fact, the choice of which method to use in this case really depends on the functions that you're given. So I repeat, if it's easier to integrate f of x, in that case, what you would do is consider the area of the rectangle and then subtract from it the area under the curve. However, if it's easier to work with the inverse function and integrate the inverse function, in that case it would in fact be easier to find the expression of the inverse and then find the area under the inverse over the corresponding interval. Now in our next lesson we're going to be tackling the area between two curves. Now this lesson was about the area under the curve. However, in our next lesson, we're going to be determining how we can find the area between two curves.